PU2 champions, welcome back to Brahmastra 2.0 series, and in today's video we are going to discuss the most important questions from the chapter D and F block elements. So you might be knowing that the model question paper is out, the question bank is out. So in this particular session we will be discussing the questions from the question bank and from the model question paper as well, and some other questions. So if you have done this particular video, all the important questions will be covered and you can revise them before your exam too. So let's get started by knowing the weightage of this particular chapter. So D and F block has a weightage of 10 marks. And how is this 10 marks divided? It is like you will have 1 marker 2 questions, okay, then you will have 2 marker 1 question and 3 marker 2 questions. So here 6, here 8 and then 10. Okay, so now let's see the questions from the model question paper 25-26. So there are 3 model question papers that is released, and we will be discussing for all the 3 model question papers. The first question: which of the following element is liquid at normal temperature? So all of we know this is mercury, because of the because there is no metallic bonding, so we have this mercury in the liquid state. So okay, by the way, this is the question paper, model question paper 1, question number 2, okay, in the 1 marker section. Now similarly for the next one, this is transition metals and their compounds are given, okay, and we have to match them. So we know TiCl4 and aluminium, this trimethyl aluminium, it is used in the manufacture of polythene, so one has to be C. So there are 2 options with 1 C. I can eliminate these 2 options. Next, if you know that nickel can be used in the hydrogenation of fat, so 3 is D. So in both the options 3 is D, 4 is B in both the options. So only thing we need to find out here is 2, right? So let us just match here what are options we have. A will be manufacture of polythene, so 1 is C, and 3 is D, that is hydrogenation of fats. 1 second. Yeah, 3 is D. Then I have a 4th, that is V2O5, and that is used in the V2O5 is used in the contact process, so 4 is B, right? Okay, so both the options 1 and 2 are exactly same, so there might be some printing error, so we don't have to worry, okay, but the answer has to be A or B. Both the options are actually correct, okay. Now let's move to the 2 marker questions. What are transition elements and given example? So this is very definition based question. This is from your 2 marker, and this is question number 25, okay, in model question paper 1. Now what is transition elements? So see, transition elements are those elements which have which have partially filled d orbitals either in their ground state or in the common oxidation state, okay. Elements having partially filled d orbitals either in their ground state or in the common oxidation state are called as transition elements. You can write any example, just one example, manganese. Definition carries 1 mark and example carries 1 mark, so total 2 marks. Next we will see 3 marker question from question number 28, model question paper 1. What is lanthanide contraction and mentions its consequences? This is the epic question of this chapter. Every year, from so many years, this question is definitely repeated, so please don't miss this question. So what is lanthanide contraction? The gradual decrease in the atomic and ionic radii from lanthanum to lutetium is called as lanthanide contraction. And what is the consequences of this? Due to lanthanide contraction, the atomic radii of zirconium and hafnium is almost same, okay. So that is why the size is similar, and that is why it becomes difficult to separate them. And another consequence is basicity decreases from lanthanum to lutetium as the size of the atom decreases, okay. Now let's see the next question. So this is question number 30 from model question paper 1 only, and here we have to fill in the blanks, the reactions actually. So the first one, you know, it is the first step of preparation of K2Cr2O7. So here we take iron chromide FeCr2O4, right, 4FeCr2O4. Then we have next question is MnO2 fused with KOH and oxidized with air. So that is for the preparation of potassium permanganate. So what do we get here in the second one? We get K2MnO4. Okay, plus water is produced, but we need the major product, that is K2MnO4. Next, third one is the heating of KMnO4. So we get K2MnO4 plus O2 plus MnO2. right? So these are the three reactions these are the three answers for these reactions, okay? So with this, we are done with the model question paper 1. Now let's move to model question paper 2 and see the first MCQ here. So potassium permanganate is a powerful oxidant. Oxidant means something which oxidizes others. So statement 1 is correct here. KMnO4 oxidizes I- to IO3- in acidic medium. Now we have learned this, that I- to IO3- happens in alkaline or neutral medium, whereas in acidic medium I- gets converted to I2. So that is why this statement is wrong. This statement is 1. So we have statement 1 is correct, but statement 2 is incorrect. That is option number D here. Next we'll move to question number 14. Electronic configuration of a transition element X in +3 oxidation state has Ar3D5. Okay, so let's write down X in +3 oxidation state is having Ar3D5. Okay, then what is the atomic number? So if you see, if I just add, what will be the configuration of X? It will be Ar3D6 and 4s2, right? So argon is 18, this is 2 and this is 6. So 18 plus 2, 20 plus 6, 26. That is your iron. Option number C is the correct answer. Okay. Now let's move to the 2-marker question. Give reason separation of lanthanoids is difficult from their neutral occurrence and study of actinoids is difficult. Now let me tell you, this study of actinoids itself can be a 3-marker question. So I'll give you answer in the form of a 3-marker answer, because last year this question itself was asked in a 3-marker section. So first of all, why the lanthanoid study is difficult? Just now we studied that due to lanthanoid contraction, the atomic radius of zirconium and hafnium is almost same. So they occur together, hence it is difficult to separate them. Okay, next is what? Study of actinoids is difficult. What is the reason for that? Actinoids are radioactive elements. Half-life of them is very small and they could be prepared only in nanograms. We don't have that much actinoids to study them because they are present in very small amount. Now let's move to the 3-marker question. Explain the preparation of potassium permanganate from MnO2 with balanced equation. Mention the gas evolved when KMnO4 is heated at 513 Kelvin. Okay, so the first is you have to find the preparation of MnO4. Okay, so first how the MnO4 is prepared? See, oxidation of MnO2 to potassium manganate, K2MnO4 takes place. So MnO2 with KOH and O2 gets converted to K2MnO4. That is oxidation of MnO2. Next, second step is the disproportionation reaction. K2MnO4 with water gives you KMnO4, MnO2 and KOH. Right? Now second question is on heating potassium permanganate, which gas is evolved? So when you heat this one, you get K2MnO4 plus MnO2 plus O2. So the gas evolved is oxygen. Okay. Now moving to the next one, considering the elements of 3D transition series, write the element which is unable to form a monooxide, having positive E0 value, a base element, Ziegler catalyst used to manufacture polythene. Okay, so first of all, unable to form a monoxide, that is your scandium. Scandium does not form any oxides. Having positive E0 value, that is your copper, you know it is 0.34 volt, and the base element of Ziegler catalyst is titanium. Clear? Trimethyl titanium we use. Next, we will move to model question paper 3. The common oxidation state shown by the elements with atomic number 21 is. So that is scandium, right? Scandium shows a common oxidation state of +3. So option number A is the correct answer here. Okay, now let's move next to the question. The actinoids generally show dash oxidation state. So this was a fill in the blanks question. So here also the answer is +3 oxidation state. Now we will move to 2-marker question with respect to first transition element. Which element has the highest second ionization enthalpy and lowest enthalpy of atomization? So if you see copper electronic configuration is what? You have argon, then you have 3D10 and you have 4s1. Right? The second ionization, so first ionization, once you remove this 4s electron, then you have to remove the second electron from D10 configuration, which is highly stable. So removing electron from here will require a lot of energy. So that is why copper will be the element with the highest second ionization enthalpy. Then lowest enthalpy of atomization, we know zinc, right? Zinc has no intermolecular bonding is there. There is no interatomic interactions. So that is why it has the lowest enthalpy of atomization. Okay. Next, we'll move to write the balanced chemical equations involved in the preparation of potassium dichromate from chromite ore. So this you have to remember. Please remember, balanced equation only you should write. So the step 1 is iron chromite is converted to sodium chromite. Then sodium chromite is converted to sodium dichromate. Sodium dichromate is converted to potassium dichromate. Okay, so these are the 3 steps of the reactions. Next, write the formula of 3 different types of compounds formed when lanthanide reacts with carbon or heated with carbon. Okay, so this is something unexpected question, or you can say first time such question has been asked. This is 29 of MQP3. So what are the products formed here? Ln3C, Ln2C3 and Lnc2. These are the carbides formed when lanthanide reacts with carbon. Okay, so this is there in the textbook, so you have to read the textbook thoroughly to answer such questions. Now we will go to the revised question bank from 25-26. What all questions are there? So 2 marker question I have taken, which is question number 3. That is, name the 3D series element having the maximum melting point and minimum melting point. So as the number of unpaired electrons will be more, there will be more metallic bonding, there will be higher melting point. So chromium is the one with the highest melting point, and zinc has no metallic bonding, so that is why it is having the minimum melting point. Next, question number 4. Why do the transition elements exhibit higher enthalpies of atomization? Very important question. Transition elements have large number of unpaired electrons, right? Due to these unpaired electrons, there is interatomic interactions and hence stronger bonding between the atoms, resulting in higher enthalpy of atomization. Next, we have the atomic sizes of iron, cobalt and nickel are nearly same. Explain with the reason. Okay, now see what happens. Let us understand the size concept. Okay, as I move along the period, okay, as we move along the period, what happens? Effective nuclear charge increases, and that is why size decreases. Right, this is one factor, but there is another factor. As we move along the period, what is happening is d orbitals are filled up. D orbital, or I can say d electrons are filled. Right, now when the d electrons are filled, okay, there is electronic repulsions. Okay, so I can say there is inter-electron repulsion. Okay, so there is inter-electron repulsion between the dd electrons. Now what will happen if there is repulsion between the electrons? This tries to increase the size of the atom, whereas this tries to decrease the size of the atom. So there are 2 opposing forces that is acting on each other. So when we reach iron, cobalt and nickel, both these factors are almost equal, and one tries to increase, one tries to decrease. The net effect remains 0 and the size remains constant. So how can you write this one? You can just explain this in this way. Iron, cobalt and nickel have nearly the same size because the increasing effective nuclear charge and the poor shielding effect of the inner d orbitals almost perfectly balance each other out. Then you can explain the terms in detail. Okay. Moving to the next question, why manganese exhibit the maximum oxidation state of +7 only with oxide? So we know that oxide, so this is question number 11 from question bank. Second question, like there are 2 marker, 3 marker section. So from 2 marker section, question number 11. So we know that oxygen can stabilize the higher oxidation states better because of its ability to form multiple bonds with manganese. Okay. Next, we have give reasons why copper 2+ is more stable than copper plus. This is in question number 15. Copper 2+ is more stable because it has higher negative hydration enthalpy. Okay, so the stability of copper 2+ rather than copper plus is due to the much more negative hydration enthalpy of Cu2+ than Cu+, which more than compensates for the second ionization enthalpy of Cu. So see, we have already discussed that the second ionization enthalpy of copper will be very high because you have to remove an electron from D10 configuration. Now what happens if you have, if this ion also gives you when this ion is dissolved, it releases also a lot of amount of hydration enthalpy, which compensates the energy that was required. So overall the value comes out to be so that is why it is highly stable. Next, why is Cr2 plus reducing and Mn3 plus oxidizing when both have D4 configuration? This is very important question. This is an in-text question, by the way. Now how to explain this one? See, copper 2 plus, okay, configuration is what? D4, as it is given already, and Mn3 plus is also D4, right? Now see, Mn3 plus, if you gain it, if it gains one electron, what it will be its configuration? Mn2 plus, right? And its configuration will be D5. Now what is speciality about D5? We all know that D5 is a half-filled configuration, right? So that is why it is stable. Now see, from Cr2 plus, if you remove one electron, we will get Cr3 plus, and this configuration will be D3. Now anything special about D3? Yes, D3 configuration is actually T2G3, right? And it is lower energy. If you remember, if you have studied coordination compounds, you know that d orbital split, T2G is there in the lower section in the less energy level, and when you have D3 configuration, 3 electrons will be filled like T2G3. So this is stable and this is stable. But here what happens? It is losing electrons, right? Means it is undergoing oxidation. So it will behave as a reducing agent. Here it is gaining electrons, it is undergoing reduction, so it will behave as an oxidizing agent. Okay, so that is why Cr2 plus is reducing, Mn3 plus is oxidizing. Now how can you write this answer? So you can write it as Cr2 plus is reducing because its configuration changes from D4 to D3, and the later means this D3 has an half-filled T2G level. Now Mn plus 3 is oxidizing because the configuration changes from Mn plus 3 to Mn plus 2, results in the half-filled D5 configuration, which provides extra stability. Okay. Next, the E0 value of copper is positive. Give reason for this. Very important question. Question number 17 here. Now see, the positive value of the copper, the reduction potential of copper, its positive value is due to very high enthalpy of atomization and low enthalpy of hydration. Okay, so these are the two reasons because of which copper is having very high enthalpy of atomization and low enthalpy of hydration, which leads to a positive value of 0.34 volt. Okay, next we have question number 8, which is stronger reducing agent, Cr2 plus or Fe2 plus, and why? Now if you see Cr2 plus and Fe2 plus, okay, the question is asked which is a stronger reducing agent, means it will reduce others, itself it will get oxidized. So Cr will get oxidized to Cr3 plus, Fe will get oxidized to Fe3 plus. Now this configuration is D3 or it is T2G3, and this configuration is D5. Now both are stable. This is T2G3, it is also half filled, but it has lower energy. Okay, lower energy and it is more stable. Okay, whereas D5 is stable, half filled. Okay, it is half filled, so it is stable, but energy wise if you see, this is having lesser energy because it splits, right? So that is why Cr2 plus Cr3 plus will be more stable, means this conversion will happen better because Cr3 plus is more stable. So that is why this is a better reducing agent. Okay, so how can I write this answer? You can write it as Cr2 plus is a stronger reducing agent than Fe2 plus. This is because the configuration of Cr2 plus changes from D4 to D3, and D3 is stable due to the half-filled T2G level. Now T2G is having lower energy. Next, we will see calculate the magnetic moment of Ti3 plus ion. This is very important question. Question number 24. It can be asked for any ion, so you should be knowing the formula. So what is the formula of magnetic moment? Root over of N into N plus Q. Okay, scandium titanium. Titanium is 3D2 4S2. Titanium Ti3 plus is 3D1. Now if you calculate the magnetic moment, so what is the number of unpaired electrons? 1. So I have 1 into 1 plus 2, that is root over of 3, that is 1.732. So option answer will, and also write the unit, that is Bohr magneton. Clear? Let's see the next question. Transition elements form color compounds, give 2 reasons. So first of all, you have to understand that transition elements, okay, the color of the transition elements is due to the presence of unpaired electrons in the orbitals which undergo DD transition. These are the 2 reasons. There are unpaired electrons and they can undergo DD transition. The unpaired d electrons absorb color from the visible region and undergo DD transition and radiate complementary color. Okay. Next, we will see the transition elements and their compounds are known for their catalytic activity. Give 2 examples. So here this can also be asked in the 3 marker sections where you have to write 3 reasons. Okay. So here you can write like what are the reasons why they show catalytic activity. That is, they have variable oxidation state, large surface area, and incomplete or fully filled, incompletely filled or partially filled d orbitals. Now examples of catalytic activity, you can see vanadium pentoxide is used for the contact process. This is one example you can write. Okay, any other process you can also write, like for example nickel is used in the hydrogenation process. Right, this example also you can write. Clear? Next we have question number 12. Iron catalyzes the reaction between iodide and the persulfate ions in the reaction. Explain the catalytic activity of catalyst iron by using the chemical reaction. This is question number 27. This is very important question, how iron can catalyze this particular reaction. So first what iron does is, that is Fe+3, oxidizes I- to I2 and gets converted to Fe2+. Okay. Now this Fe2+ which is formed, okay, it reacts with S2O8 2- and Fe2+ comes back as Fe3+ and S2O8 is converted to SO4 2-. So you can see the catalyst is regenerated in the reaction and it also catalyzes the reactions. Okay. Now let's see the next question, characteristics of interstitial compounds. This can also be asked in a 3 marker question because we know 2 to 3 properties can be written. So 2 properties, 3 properties, it can be interchanged and asked. So first is they have high melting points, chemically inert, and retain the metallic conductivity. Okay. Next we will see what is the composition of mic metal and write one of its use. So mic metal is a alloy of lanthanoid where we have 95% lanthanoid and 5% of iron and traces of sulfur, carbon, calcium and aluminium. Now what is the use of it? It is used in the magnesium based alloy to produce bullets, shell and lighter flint. Okay. Next we have draw the structure of dichromate ion and what is the value of bond angle of CrOCr in it. Okay, so dichromate ion, you can see Cr2O7 2-, this is the order, and the angle, the bond angle here is 126 degree. Okay, so please remember, and the structure also. Now we will move to the 3 marker questions. Give the general. So in 3 marker question, definitely you will get the reactions, or will get the what it is, the preparation of K2Cr2O7 and KMnO4 and the catalytic properties, or the interstitial compounds, or why they form complexes. Such type of reasoning questions will be asked. One question. Another question will be from the lanthanoid sections. Okay. So first give the characteristics of lanthanoids. This question was asked in many times. So lanthanoids are silvery white metals. The first thing, their hardness increases, they are good conductors, and they show +3 oxidation state, and lanthanoids can also show colors and they are paramagnetic in nature. So basic properties you can write down. Next question is, what is actinoid contraction? Actinoids show greater number of oxidation states. Why? And what is the common oxidation state of actinoids? So actinoid contraction is same as lanthanoid contraction. The only thing is the orbital will change here. So the steady decrease in the size of the actinoids across the actinoid series is called as actinoid contraction. Now what is the reason for this? Why do they show greater number of oxidation states? Because here the energy, the orbitals which can participate in the bond formation are 5f, 6d and 7s, and their energies are very less, means the energy gap between them is very less. So all the electrons present in these orbitals can participate in the bond formation. Next, what is the common oxidation state of actinoid? So actinoid shows a common oxidation state of +3. Clear? Okay. Next, we will see why cerium shows +4 oxidation state, what is the highest oxidation state shown by actinoids, or name the elements that shows the highest oxidation state among actinoids. So what is the highest oxidation state? That also we will discuss. So why cerium shows +4 oxidation state? See, cerium configuration in +4 is exactly the configuration of xenon, which is a noble gas configuration, and that is why it is highly stable. Next, what is the highest oxidation state shown by the actinoids? It is +7, and which element shows that? Neptunium and plutonium, okay, Np and Pu. Next, we have 3 characteristics of actinoids. You can write down. They are very radioactive, they are silvery metals, highly reactive, paramagnetic in nature, and they have also shows actinoid contraction. Next, any 2 differences between lanthanoids and actinoids? This is also a very important question. So here in lanthanoids, the last electron enters the 4f shell. Here it enters the 5f orbital. There is no radioactive except promethium. Here almost all the elements are radioactive. Then we have, they are less basic, they are more basic. Then 4f have greater shielding effect, 5f have poor shielding effect. Lanthanoid contraction is lesser, actinide contraction is greater. So any such examples you can write down, any 3 points you can write down. Okay. Next, study of actinoids is difficult. Give 3 reasons. Already I have discussed this one. They are radioactive elements and their lifetime is very short, and they can be prepared only in nanograms. So it is very difficult to study them. Okay. So students, these were the most important questions from the chapter D and F block. So prepare these questions thoroughly, repeat these questions again and again, write and practice them, then definitely you will be mastering this chapter. Okay. Thank you so much, my dear children, and I hope you liked this session. Put down your comments, any doubt, I'll be definitely answering them. So thank you and all the best.